to do a video on drawing scale diagrams for vector addition. So in this video, we will be drawing vectors in 2 dimensions. General rules for this: when you're drawing vectors in 2 dimensions, you draw one vector and then you draw the other one tip to tail. So you draw one and then the other one coming off. If they are in the same direction, you can resolve that usually using directed numbers, positives and negatives. But if you are doing in 2 dimensions, so like for this example, we had 2.2 meters south, 1.8 meters north. All right, that I drew in centimeters, and then the resulting vector goes from the start of the first to the end of the second, and you can just figure it out. If you've gone 2.2 meters south, 1.8 meters north, you've gone 0.4 meters south. All right, but not so easy when it comes to doing in 2 dimensions. So the second example, we got 220 meters north and 80 meters west. You need to draw that as a scale diagram, all right, which we're going to demonstrate in a minute. And you can see here I've gone and drawn that as a scale of 1 to 50, converting centimeters to meters. So that's 4.4 centimeters. I don't remember what I wrote there. It doesn't look like I've written it down, but the resultant vector goes up to the left there, and I measured that angle 20 degrees. Okay, so let's go through an example so you can watch how this process is done. We're going to go through. So in my solutions, I've gone through and done all the questions there with examples in both trigonometry and scale diagrams. All right, but I need to go find the other one because I've lost my questions. Hold on me a moment. Okay, so I found the questions. Okay, I'm going to pick one of the harder ones. So question 6, it has some large numbers that we're obviously not going to convert to 1 kilometer to centimeter scale. We have to do some division to make that happen. So it suggests using 1 centimeter every 100 kilometers. Yeah, that's what we probably have to do. But we could actually pick something different. I might do something different for the sake of this operation. All right, so I have got my document camera here and a piece of paper so I can actually demonstrate how I go about doing this. Now, tools of the trade, obviously pencil, first and foremost. Make sure your pencil is sharp. Always good to have a sharpener with you. And just make sure your pencil is nice and sharp. Okay, that's important. All right, in case you make mistakes, eraser. All right, now you can either use a geoliner, that's a protractor, and this is the geoliner. All right, so my geoliner is a little bit broken, but it's still actually better than my protractor, because we've got a bunch of markings on here. If you notice that you have markings that go along this way and markings that go across this way horizontally. They are always at right angles to each other, so that's very handy when we want to try to make something that's at right angles to what we drew before. All right, also got a general rule in case I want to draw longer lines than what I can fit on here. Okay, so let's write down what we know for the question. So we've got question 6. Where is my... Okay, shuffle my page a bit. I'll find where I am on the screen. All right, so question 6. So what do we know? Okay, so Alan rents a private jet for the weekend. He flies 400 kilometers south to New York and then flies 700 kilometers west to Chicago. Okay, and then 1,200 kilometers south to Miami. So let's just think of the vectors we got here. So we got, all right, so we got 700 meters. Sorry, kilometers. First use my eraser so far. Yeah. Oops, I am actually going to do them in order to start off with. All right. Okay. There we go. All right. So we've got 400 kilometers south. We have 700, so we're going to add 700 kilometers west. Okay. And then we've also got Okay. All right, 1,200 kilometers south. Now, one of the neat features of vector addition is just like your scalar addition, you can actually change the order to make the question easier. And that's what I suggest you guys do. And you can also add them in any order such. You can add the first two or the last two. So what we're going to do, we're just going to change these ones because they're in this. I'm going to move the last one to the second one because they're in the same line. They're actually in the same direction as well, which makes it even easier. Okay. And then I'm going to add that one. Generally, my suggestion when you do these questions, if you have a north or an up in your vector, a north-south, up or down, make that the first one you draw because you're going to have to draw your resulting vector off that. So what we're going to do, we're going to simplify these first two because they're in the same direction. If you go 400 kilometers south and also go 12,000 kilometers, so 400 and 1,200, 1,200, you are traveling a total of 1,600 kilometers south. Okay, so by doing this, we actually only need to draw two vectors now. In some of my examples, I've actually drawn all of the vectors, but I did them in this sort of order. So I draw south, more south, and then west. In this case, I'm just going to draw the two of them. So I'm just going to draw a long one going south, and then the shorter left one going west. Okay, so now we've got to think about scale. So they suggested doing 1 centimeter to every so 1 centimeter is 100 kilometers. I don't think I'm going to fit 16. I'm not going to be able to fit 16 on my screen. So I'm going to make mine a little bit smaller. So my scale, if I do 1 centimeter is every 200 kilometers, then I'll need 8 centimeters to get there. And I think I'll be able to see that on my screen. All right. So my scale, I'm going to write it here, is going to be 1 centimeter represents 200 kilometers. All right. So let's just write, and I'm also going to just write a little note here. Haven't done this for all my solutions, but since I'm doing the video, if I'm going to go and divide that by 200 for the sake of my scale, all right, so that's going to become 8 centimeters, and the 700, if I divide that by 200, okay, that's going to become 3.5. All right, so I should be able to fit that in the space I've got available on the screen here. All right, now, probably helpful if you don't see, I'm actually using a blank piece of paper because I decided to do this on hard mode. All right, but I have the right tools. If you have no grid or no lines in your page that you can measure off, you're better off than drawing something to represent north. So I'm going to draw a line. It's going to be just a reference line. This is going to be my north line. Okay, so it may not be entirely vertical at the page, but everything I'm going to draw is going to come off that. And with my geoliner, I can actually line that up. See, I can just move this across and just line up the parallel lines. And then I can go and draw south anywhere I like because I've got this lined up with that north line I just drew. Okay, so I want to draw something going, we want to go 8 centimeters south, which would be down the page. Okay, so shift my little one here, get a position where I can fit this in. So I need to go from, if I'm doing 8, I need to go from 5 to 3 down here, which you won't be able to see. All right, I might just shuffle that out a little bit more. And then I can go from 6 to 2, which is a little bit below where we can see here. I might need to adjust my camera in a moment. Okay. Right, now I've drawn that a little bit too long. So I'm going to rub off the end here. Okay. All right, I'm going to shuffle my camera a little bit. Okay. There we go. All right. So I'm going to measure that off the 7. Okay. That's still a little bit longer than I want it to be. Okay. All right. So I'm going to put a little arrow. So that end of that arrow is now precisely at 8 centimeters. So I measure that again. All right. So if I go from 6, and that end is right on 2. I might just be off by about a millimeter. All right. But that's a decent enough job for this. All right. Now I need to go across 3.5. So what I'm going to do, I'm actually going to turn it around and see I'm lining up that south line with this line here. So when I draw across, it's going to be at right angles, which is what I want. Okay, I might even, no, I'll stick with that. So I'll draw off the 0 point. Now I must draw this off the tip of the last vector. Give it a little bit of space to fit your pencil in there. All right, so we go to 3.5, which is there, and then draw across. Okay. All right, so there's my west. Okay. So there's my 2 vectors. All right. Now I'm going to draw, I've got to draw a line starting from the start of the first to the end of the second. Okay, so there's my line there. Okay, and there's my vector. That's my resulting vector. That's the actual displacement there. I was about to write an X. I want to write an S for displacement. That's my displacement there. So we'll find out what that is in a minute. I'm also going to measure off the angle. Okay. All right. Now you may have a geoline or a protractor. Just be careful where you measure from. If you notice here, you've got to measure an angle off that intersection. If you're using this, there's a common one most of you have, or most of you have available to you in your classroom. Make sure you put that crosshair over the top of that join, line up so it's nice and it's parallel with the first vector, and you measure across. So you measure across, and I am reading that at 21, 2, 3, about 23. All right, if you're using a protractor, okay, the crosshair is there at 0. Just be careful when you measure form. I find it easy to read the ones on the inside rather than the outside. So just be careful of that. And make sure your lines are going long enough. You may need to extend them beyond the actual vectors. Draw little soft extension lines if you need to. All right, so again, line that up with the corner. Okay. And I'm getting a different reading. That is a bit interesting. Double check my results in a minute. Okay, so that one I'm getting closer to about 29. Reading off that one, unless... No, I think actually I have the crosshair wrong. I must be reading off there. Okay, sorry, not that point there. You can see that actually starts at around almost 10. There's a missing, the 0 is missing here. So sorry, you've got to measure to right from the end of the device if you're using this. And now we're getting about the same results. We're getting 23. So yeah, you have to measure from where the 0 actually is. Imagine there's a line coming off. So probably in this instance, actually your geoliner is actually better at, your protractor is actually easier for reading angles than your geoliner is. All right, so that one was about 23. So we put that in the angle about 23 degrees. All right, now the distance. Okay, I might just pull out my actual ruler. I can measure that nice and good. All right, so okay. Put that right on the end. Okay. So about 8.2. Measure it the other way just to be double sure. Went through there. Yeah, I'm getting that a bit longer actually. Don't think I was going to line that up right. Line up with the point. Yeah, a bit more like 8.7. All right, I'm going to write that 8.7. So the distance there, 8.7 centimeters. Okay, that was 8 centimeters, and that was 3.5 centimeters. Okay, that's what the scale is. So what is the actual displacement then? Well, we scaled everything down by 200. Now we have to scale it back up. So 8.7 times by 200 would be, now another piece of device you should be using is a calculator. Now I could probably do that in my head. It would be something like 17. Well, times by 2, 17.4 times by 10. Yeah, times by 10 again. 1,740. Let's check. Did I get that right? 8.7 times 20. Yep. Okay. All right. And then that was in kilometers. So that's the magnitude of displacement. Now, the displacement itself, okay, 1,740 kilometers. Okay. Now, I prefer to use this kind of compass bearing method. So I measured, you must also measure off something. So that 23 is measured off the south line. So I'm going to write south, 23 degrees towards the west. Now, if you use true bearings, remembering we also measured the south off the north. So if you add another 180, an alternative unit would be at 180. So it'd be 203 degrees true bearing. There's also another way of representing that. All right. So that's the answer for that. Now, what I'm going to be demonstrating next is we're going to check that using Pythagoras. So if you're a bit rusty with your Pythag, okay, so Pythagoras and trigonometry. Pythagoras we're going to use to work out the missing length of the other two. So remember, if your triangles could be labeled A, B, C, where C is the hypotenuse, the longest line, because that's your right angle and the relationship between the sides of angles and the opposite lengths. All right, so the way to get displacement is C squared is equal to B squared plus A squared. Now we're going to go back to our original values. So C squared equals, now some of you, you're welcome to skip ahead if you are bored because you know how to do this. Oops, actually not the original. Apologies. We just want the total the total south. Okay. Total south and the total west squared. All right, so add those up. This one we will need our calculators. I can't do square roots in my head. Not large ones anyway. Okay, and then take the square root of that. Okay, so C squared was equal to, okay, I think that's right. Yes, that's right. All right, and then shuffle my camera down a little bit. Okay, and then take the square root of that. Okay, so you notice that I got a little bit off. Like my answer here is a little bit off. That's to be expected. Realistically, you would realistically only ever achieve about 2 to maybe 3 cent figures. I'm off at the third because that would actually round off to 1,750 if I rounded off that number. So I'm a little bit off, but that's probably as good as you're going to get for a scale diagram method. This is the expectation we're going to have. If you do something with scale diagram, we're expecting your answer will be an estimation in comparison to doing it a more mathematical method like Pythagoras. Okay, let's also double check the angle. Now, just remember your right angle triangle. So maybe just go back a little bit. Okay, relative to this angle, the length that we started with was the opposite and the adjacent. And if you remember your acronym SOHCAHTOA, okay, so sine is the sine of an angle is opposite over hypotenuse, cosine of an angle is adjacent over hypotenuse, tangent of an angle is the opposite over the adjacent. If we had the opposite and the adjacent, we should be using tan. That would read like this: tan of that angle is equal to the opposite. So the actual opposite was the 700 divided by, or over, okay, move my page a little bit. Okay, divided by the adjacent, which was your 1600. Okay, all right. Move my document cameras again for a bit more space. Okay, all right. Divide those and use the inverse tan function. So I'm just going to do this in one hit. Inverse tan 700 divided by 1600. Okay. Okay, inverse tan, bracket, 700 divided by 1600. Okay. Okay, so that was about 24 degrees. So 23.6. I'll write it through some figures. Okay. So the actual answer would be approximately. We are still rounding things off. All right, so I'm saying 1,746 kilometers in a direction of. All right. I'll round it here. I'll round to 4 cent figures since I got 4 here. All right. So in the direction of south 23.63 degrees towards the west. Okay. As expected, yes, that's so this method, yeah, about 2 cent figures. I got 23. It actually rounds to about 24. When you're considering that this is out of the 360, it's the scaling, it's actually not that bad to just be off by 1 degree, because only 360 degrees to work with, whereas these scales can be whatever you like, depending on the size of the problem solving question. So yeah, so I'm a degree off. So correct to 1 cent figure, a little bit off. And then that one I was correct to about 2 cent figures, with the third one being a little bit off. So yeah, the expectation is scale diagrams, you're only going to get a limited accuracy. If you made your diagram really, really big and you use really, really fine tools, you could do it better. But the idea is this: you're meant to be able to just do a quick little sketch without too much hassle and work it out. So the option's up to you. Do you want to do it with a scale method, or do you want to do the Pythag way? And the expectation is we're going to look at the solution. And if you use a scale diagram, there is understanding in terms of just how accurate you're actually going to be able to achieve. All right. So whereas using the Pythag way, you do have to remember these Pythagoras and trigonometric rules, but you will get a little bit more accuracy in those. So up to you which one you want to use, so long as you can competently use a method to find the resulting vectors from the addition of 2 vectors in 2 dimensions. All right, I'm going to leave the video there. Thank you for watching.